Hey everybody. So I wanted to make a quick video. Somebody asked me about graphing space curves. And so this problem in particular. So I'm given the curve, the vector function R of t is t cosine t, t sine t, and t. And there was a hint given that it lives on this surface, x squared plus y squared equals z squared. So before we get into it, I want to just say, right, I use GeoGebra and other graphers in multiple videos that I've made. And so a reasonable question to ask might be, why in the world would I graph something by hand? And the answer is the same reason we learn graphs all through our math career is there's lots of reasons. One of the main reasons I believe in is that it builds our intuition about how functions behave, right? These are a new kind of function. And we might be able to perform some of the like algebraic steps or some of the derivatives and things like that we do on them. But it probably takes some time to develop the meaning behind them and some interpretation. And we just have to kind of spend some time digging them apart. And graphing is a great way to do that, to start understanding what these curves are actually telling us. Okay, so remember, this is a vector function pointing at points on a curve, and we kind of go back and forth between thinking about vector function and then thinking of those actual points C. So what I'm going to actually graph is the curve I'll call C, which is all the points that this vector function points at, right? Drawing all those arrows pointing at all those points wouldn't be very informative visually. It would turn into quite a mess. So let's begin, and the hint was to see that it lives on this surface, and then maybe start exploring this surface a little bit. So let's follow that hint, right? So first of all, to show that it lives on the surface means to say, show that every point of this curve, right, or every point that this vector function points at lives on this surface, means that every point satisfies this equation. And so what we want to show is that no matter what value of t we put in, this relationship is satisfied, okay? So the easiest thing to do is say, well, I just need to make sure that it's always true that this x coordinate squared plus this y coordinate squared is equal to the z coordinate squared, because that's what this surface is, all the points with that relationship. So let's go ahead and do that. We have t cosine t squared plus t sine t, oops, that's not the t, squared equals our z coordinate, which is t squared, right? So I've just substituted in the x coordinate, the y coordinate, and the z coordinate. So let's do a little bit of algebra. We get t squared cosine squared t plus t squared sine squared t equals t squared. We can factor out t squared. Equals t squared, and then of course cosine squared plus sine squared is just 1, so we end up with t squared equals t squared, which is true. And so this is always going to be the case, right? None of these algebraic steps we took depended on a particular value of t. And so what that tells us is the points on the curve associated to this vector function live on this surface, right? The surface is likely going to be many more points, but we're looking at some set of them. So let's try to get a sense of what this curve looks like. This surface looks like. And this surface is pretty straightforward to uncover, to figure out what it is. So one of our methods we've talked about is traces, where we imagine what happens for particular values of one of these variables, right? This is similar to if I gave you something like, well, let's use something that's going to be useful in a moment. Let's say I gave you the equation in 2 dimensions, x squared plus y squared equals 4, right? We might recognize this as a circle, right, with radius 2, centered at the origin. But if you didn't know and you wanted to start figuring out what it looks like, one of the things you might do is say, well, let's start finding some points on this graph. And you might say, what happens when y is 0? And you get, oh, x squared equals 4, so x equals plus or minus 2. And you come over to your graph and you say, okay, x can be 2 when y is 0 or negative 2. And then maybe you come back for letting x equal 0, and you find that y can be 2 or negative 2. And so you're plotting points for each value, right? These are like kind of like our traces in 2 dimensions. I let each variable be a value and see what the other one has to be, right? If x is equal to 1, we get 1 plus y squared equals 4, and then y has to be plus or minus the square root of 3, right? So then I would get points like this and this. And if you do negative 1, you get points like this and like this. And so as you plot these points, you begin to uncover, oh, this thing's a circle, right? So that's the same method we're trying here. It's just when we take one of our variables and let it equal a constant, instead of getting points, we get curves. And we try to stack these curves together, like stacking up these points and seeing if we can get what's happening. So let's do that. We'll do traces for x squared plus y squared equals z squared. Okay. And you can do a little bit of experimentation, but the thing that jumps out at me is that this half of the equation, right, looks just like the example I gave. That's most of the equation of a circle, where this side would be the radius square. So if I take a trace, for instance, for, let's say, z equals 0, I get the equation x squared plus y squared equals 0. This is going to have exactly one solution, the point 0, 0. So if I start, well, what I usually do if I'm doing traces where I'm letting z equal some variable, I'll look at x and y. So at the level where z is equal to 0, the curve or the surface only has one point, the origin, right? Let's look at z equals 1, then we get x squared plus y squared equals 1, right? Well, this is a circle with radius 1, center at the origin. If z were equal to 2, we'd get x squared plus y squared equals 4. Well, we get a circle with radius 2, right? So these don't exist in the xy plane. The point in the middle is living in the xy plane in our 3-dimensional system, because that's when z equals 0. By the time we go up until z equals 1, the trace of our surface is a circle that's gotten bigger. By the time we get up to 2, it's gotten even bigger, and you can quickly see what's happening. Whatever the z value is gives us the radius of the circle that our trace is, right? Z equals 3. And also notice it's going to do the same thing in the negative direction. If z was negative 1, this would look exactly the same. Negative 2, this would look exactly the same. So what does that mean? Let's expand this drawing to 3 dimensions. What we're trying to say here is this. If I have x, y, and z, right? Well, when z was 0, that's in this xy plane, our surface was just 1 point. By the time we got up to z equals 1, right? So we're now up above the xy plane, we end up with a circle of radius 1. If I go up to z equals 2, I get a circle of radius 2. Z equals 3, I get a circle of radius 3. And the same thing was happening in the negative direction. As we go down the surface, we're getting larger and larger circles. And so if you can imagine what shape would do this, right? My drawing's not perfect, but we would have a cone like this, right? So let me just try to sketch it without all the extra information, right? This is what our surface looks like. Of course, it's extending forever. I've kind of had to end it. But if you imagine taking, when we took a trace, we were slicing at levels of z. We sliced at z equals 0, there's just a point there. When we sliced a little higher at z equals 1, there's a circle. When we sliced a little higher, there's a bigger circle. And as we slice higher, there's even bigger circles. And as we went in the other direction, we saw the same thing, right? So that's how we're using these slices to construct what this thing looks like, right? Sometimes you need to slice in multiple directions, letting x and y equal some values, but I think in this case, that was enough, right? This stacking of circles, and it's pretty clear to see for any value of z, like here's the 4, but, sorry, z equals 2 gave us a 4. It's really just saying if z equals r, the radius of the circle, we're just, the value of z is the radius of the circle, right? And that's what we see over here. So what we know now is that whatever our curve is, and we don't know what it is yet, it does whatever it does on the surface, right? I've drawn some arbitrary curve that lives on the surface of this double cone, or whatever we want to call it, okay? So it helps us, but it hasn't finished the problem for us, okay? So let's put this in the back burner for a moment and now approach the space curve a little differently. Okay, so we're going to use this information in a few minutes, but we're going to do some other work first. So let me just remind us of our curve. R of t equals t cosine t, t sine t, and t. Okay. Let's simplify our problem for a minute. Let's try to examine this ignoring the z direction. Okay, so I want to, and I'm going to kind of pull back from the vector function and think about parametric equations. So I want to think about the parametric equation t cosine t, t sine t, okay, in 2 dimensions. And let's think about the set of points this traces out. So first of all, we should notice that if we ignore those 2 t's at the beginning, we're looking at the graph, we're looking at the equation, the parametric equations for a circle, right? All the points of these parametric equations, and I'm taking the domain to be all values of t, all real numbers. The parametric equations without the t's, so maybe I'll write it below, cosine t, sine t, we recognize as tracing out a circle with radius 1. Okay. However, that's not what actually happens. We're multiplying by t, but we can use this picture to figure out what happens here. When t equals 0 for these equations, we start right here and we move in this clockwise direction, counterclockwise direction, right? So what's going to happen? When t equals 0, if we had this set of parametric equations, we'd be out here, but we're multiplying x and y by 0, so this x coordinate of 1 becomes an x coordinate of 0, right? As we increase t, right, without the coefficient of t in front, we'd be moving around this circle, but what's happening instead is we're tracing out this circle with an increasing radius. We're starting with a radius of 0, and as we circle around, our radius is getting larger, right? By the time we're pointing straight up, we would originally have had be up at the point 0, 1, but we've multiplied, right? This happens at pi over 2. Pi over 2 is about 1.5, just a little bit bigger than 1.5. So we're somewhere up here. In other words, we're getting an ever increasing circle, right? So we're not getting a circle. I'm just kind of using it as a metaphor. We're going to circle around, but our radius just keeps getting larger. Okay? So that's in the positive direction. Now let's think about what happens in the negative direction. This one's a little bit trickier. Okay? Again, starting from this point, using this purple circle as like, the purple circle gives me my direction, right? As I decrease t, I'm going to be moving around in this clockwise direction, but then I'm multiplying by t, which will change the radius. The other trick that happens here is the following. Let's kind of do the same game we did here. As I move in the negative direction, the original, the purple, the unit circle, for instance, when I've moved a little bit in the negative direction, would want to be out here. However, I'm multiplying by a value of t, so I'm changing the scale of that, but I'm also multiplying it negative, which means we move in the opposite direction. So instead of being down here, the radius is going to go this way. And so by the time we move down to negative pi over 2, the radius of this circle has moved us down to here, except the negative means we go in the opposite direction. We're actually up in the same place. We're going this direction. Okay, so we get this kind of mirror image of what's happening. Okay, so this is what our curve is doing if we ignored the z information. Let me do one more thing to this graph. I'm going to color the negative direction blue. Oops, not doing a very good job here. I should have thought of that first. Okay, so if we now can imagine that cone shape we just drew coming up out of the page, the red curve would be sitting on that cone, and this blue curve would be on the cone that's moving down from the origin. So let's see if we can sketch something to represent this. So here's x, y, and z. So let's draw the surface. Let's just do the top half so the image doesn't get too. So here's my cone. Okay, so here's x, here's y. Now, remember at z equals 0, we're right in the origin, right? So I'm going to follow this, this red curve as we move up, okay? So I'm starting out, I can think about starting out pointing in the x direction, and that unit circle that I used, this purple one, we can think of as living in the xy plane down there. By the time I rotate around to pi over 2, right, I'm at this point up here. I'm going to do this part of the curve, but it's also increasing its z coordinate the whole time. So it lives on the outside of this cone, wraps around the back of it. Now I'm back around the front of it. We're getting this widening set of circles that lives on the outside of that cone, okay? I know it's tricky to see, right? And the point of this is I'm not trying to produce the world's most perfect graph. We do have computers that can do this, which will make it all much easier to look at, but I'm trying to understand how these things work, right? The cosine t, sine t part is sending this thing around a circle. The t in front of them is making those circles get larger and larger as we go. In the negative direction, there's that extra fact that they're switching the direction that they point because of the negative. And then the t coordinate is making this whole thing, right, that would be happening in a flat plane. We just start lifting it up as we go. And that's how we get this, this cone with this kind of spring coiled around it. So let's take a quick look at a much better rendering of this than I can accomplish. Okay, so here's the surface, right? Our cones. You can imagine, let's actually just do a quick slice. For instance, at z equals 4, there's the plane z equal 4, all the points with a z component of 4, a z coordinate of 4, right? And you can see it slices it in a circle, whichever way we look at it, okay? That was the traces we were doing. Turn that. Now let's add the curve. And now we can maybe see a little bit better what I was trying to explain, that we see this spring coiled around. That's as far as I've graphed it, to 2 full rotations in the up and down direction. Let's look down the curve. So let's get oriented. Yeah, here we go. This is our traditional orientation with the positive x to the right, the positive y up. The solid black line is the positive direction, right, that we had drawn. And then the dotted ones are going down below the surface. That's why they're dotted. And we see that curve that we sketched when we had negative values of t, right? So here, when we look at it in this view, when we're looking down the z-axis, it's like we can't see the z information. We've removed the z coordinate. We're looking at it in the plane, right? Without that surface, we see that graph that I made, okay? So that's the idea, right? There's no shortcut to understanding these graphs. Then, I mean, you're think back to learning how to graph in it probably might escape your memory, but in the very beginning, one of the exercises we typically do is we just plot points. You plug in numbers, see what the other value comes out, right? When you learn how to graph y equals x squared, you put in values of 2, compute values of y, and plot those points. That's basically what we did here. Right? We didn't know what this thing was going to do. We don't have a catalog of functions in our head that we can apply transformations to. We're building that catalog, right? So the one thing we kind of have right now is seeing that circle cosine t, sine t locked up in this thing, and then we had to manipulate that, right? But it's going to take a lot of just brute force work right now, right? Plugging in values, computing things, one little piece at a time, slowly constructing this, okay? All right, that's it for this video. Thanks, everybody. I will see you next time.